right? Units of measurement. So in chemistry, units are ways for us to communicate, right? And for us to measure, right? So units are standard quantities used to specify measurements. There are two common unit systems. We got the metric and the English system. The metric system is used in most of the world. Unfortunately, we use the English system. And we're kind of stubborn about it too, because a lot of people are trying to like change it, but we're like, nope, we're gonna stick to the English system, which actually, you know, um, I feel like it hinders us, right? It's harder for us because everybody else is in the metric system. We always have to constantly convert from English to metric, right? Which is not convenient. But we can do it. We'll learn how to do that, right? So scientists, we use um what's called the SI system. It's the International System of Unit, and it is based on the metric system. The SI comes from the French phrase Système International des Unités, and that is right, that's what SI stands for. And these are the 7 standard units. Let's go through them and also the symbol. This is really important that you guys not just know what is it measuring, but also the symbol, right? So the 7 things that we measure in science, right? Length. The unit there is the meter, okay? And it's a little m for the symbol. We measure mass in the unit of kilogram, and it's little k, little g. Okay. We measure time in the unit of second, that's little s. Temperature, we measure in Kelvin, big K. Amount of substance, we measure in mole, and the symbol is MOL, all lowercase. The casing is very important, okay, guys? So I want you guys, when you write these things, make sure that you have the right case, right? Uppercase, lowercase. Electric current, amperes, capital A. You're not gonna see this in the class a lot because this is more for physics later. And then luminous intensity, it's the candela, little c, little d. Also, you're not going to see that in this class, right? And so you're going to see mainly the top 5 base units there. Okay. And then we're going to combine these units too into more complex units, but that's why they're called the base units, right? It's the simplest units. Okay, so let's go through the base units in more detail and kind of see like how do we keep track, right? How do we like standardize these measurements? So the meter is slightly longer than a yard, right? In the US, we talk about yards, right? So 1 yard is 36 inches, while 1 meter is 39.37 inches. So meter sticks slightly longer than a yardstick. And it used to be measured as 1/10 millionth of the distance from the equator to the North Pole through Paris. Can you imagine like who walked that to figure that out, right? It doesn't, and also doesn't seem very accurate, right, to define it that way. And so, um, as we've gotten more sophisticated with our instruments, we now measure the 1 meters as exactly the distance light travels through a vacuum in a certain period of time. That's 1 over this number, right? And so you guys see what this number is? That's 2.99 times 10 to the 8th. What? 3 times 10 to the 8th? If you round it, that's the speed of light, right? So 1 over that is going to be meter, okay? The kilogram it's a mass, right? So the mass of an object is the measure of how much matter is in there, okay? And the SI unit for mass is kilogram, right? If you want to convert it to, what we're used to, 1 kilogram is 2.205 pounds, right? Another common unit is gram too, right? If you have a smaller amount, you can measure in just gram versus kilogram. And, 1 gram is 1/1000th of a kilogram, right? So 1 kilogram is 1,000 gram, okay? So the weight of an object, how's that different than the mass? Well, the weight of an object uh, uh, accounts for gravitational pull on the matter as well, right? So the weight of an object is going to be, always bigger than the mass, right? But that's the difference. And I know, like, when we're just speaking, uh, we use those interchangeably, but it's important to know that there's actually two different things, right? Mass is the measure of the quantity of matter that's within it, and the weight is taking into account also the gravitational pull, right? So, when people say, oh, I want to lose weight, that's actually not what you want to lose, right? You actually want to lose mass. Because you can lose weight by doing very simple things like jumping into a swimming pool. You've already lost weight. That's not what you mean, right? You mean like, oh, I want to lose mass. Right? I want to get smaller. Okay, so the kilogram, there's a standard. Okay, there's a standard that's kept under guard in France, under a double bell jar. And in order to handle it, you need gloves, you need these forceps. It's very sensitive, right? Can you imagine if, the kilogram somehow gets a speck of dust on it or gets, a piece missing from it? Our standard kilogram cannot either gain or lose weight, right? That would be a disaster. And so that's why the original actually, no one ever touches it, right? It's only in the very special cases that it's going to like get use at all. There, so instead, what happens? They made 7 prototypes from the original, and they sent it to different spots in the world. So our standard kilogram is kept at the NIST in Colorado. So that's how we agree, right? Worldwide, what a kilogram is. Okay, the second, that's the measure of the duration of an event. So as a unit is seconds. Okay, so 1 second is defined as the duration of 9,192,631,770. Okay, a lot. Periods of the radiation emitted from a specific transition in a cesium-133 atom. Okay, so as we get more, sophisticated, we can just actually measure the duration of the radioactivity, basically, of the cesium-133 atom. Okay, the Kelvin. This is a measurement of temperature. Okay, big K. So the temperature is a measure of the average amount of kinetic energy of the atoms or molecules that compose the matter. Temperature also determines the direction of thermal energy transfer, and what we commonly call heat. Okay, so energy transfer is always going from hot to cold, right? Where there is more heat to where there is less heat. It's always from hot to cold and never the other way around. Okay, so you know, when I was younger, I had this misconception of like, oh, if I touch like an ice cube, then the cold is being transferred to me. That's not why I get cold, right? If I touch an ice cube, it's because the heat from my hand is being lost to the ice cube, right? That's the direction of flow, and that's why I feel cold because I don't have heat anymore, right? So the Kelvin scale um, assigns 0K to the coldest temperature possible, okay? So now if we compare that to the Celsius and the Fahrenheit, you see that's 3 thermometers here. Now in science, right, we use the Celsius and Kelvin scale, and that's actually really easy because the difference between Kelvin and Celsius is just a shift of 273.15 Kelvin. Okay, so 273.15. So what all you need to do is, either add or subtract that number, right, to go from Celsius to Kelvin. Now, from Celsius to Fahrenheit, you see the gradations is actually very different. So it's more complicated to try to convert from Celsius to Fahrenheit, but we do have a formula for that, which is on your uh, 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 conversion sheet. Okay, so you don't have to memorize this. Okay, you just have to know how to uh, uh, utilize the equation, right? So again, if you want to go from Celsius to Kelvin, what you do is you add 270.15, and I do want you guys to use all 5 numbers here, all 5 sig figs, okay? 273.15. And if you want to go back, then you subtract, right? If you want to go from Kelvin to Celsius, then you subtract 273.15. And here, if you want to go from Fahrenheit to Celsius, what you do is you take Fahrenheit minus 32 and you divide by 1.8. Okay. And then if you want to do it the other way around, right, you just do algebra. Okay. So if you algebra this, let's see, what would we get here? Let me switch to the board real quick. And So what we had before was Celsius is equal to Fahrenheit minus 32 in parentheses divide by 1.8, right? So if you want to change this and you want to solve for Fahrenheit, then you need to multiply by 1.8 to each side, okay? So that'll cross this out, you get 1.8 degrees Celsius times Celsius is equal to Fahrenheit minus 32. Now, if you want to get Fahrenheit by itself some more, right, you need to add 32 to each side. Okay, so in the end, right, minus 32 plus 32, that cancels. So Fahrenheit is equal to 1.8 times Celsius plus 32. Okay, so those would be your two equations here, right? One is going from Fahrenheit to Celsius, and the other one is going from Celsius to Fahrenheit. Okay. Let's get this slide back up. All right. So yeah, we can do this one together now. Gallium is a solid metal at room temperature, but it will melt to a liquid in your hand. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and the Kelvin scale? Okay, so let me erase the board. We'll work that out together. So 85.6 degrees Fahrenheit. What is the temperature in Celsius scale? Okay, so we're going from Fahrenheit to Celsius. So remember the formula, right? We have okay. Right, so we want to know what Celsius is. We have the Fahrenheit, we just plug it in. So this is 85.6 minus 32 over 1.8. Okay, so right, so just punch that into your calculator. So 85.6 minus 32 divided by 1.8. So we get 29.8 Celsius. Okay. And then it asks us to convert to Kelvin. So how do we go from Celsius to Kelvin? Well, we add 273.15, right? So 29.8 plus 273.15 give us 303 Kelvin. Okay, so that'll be our two answers there. Okay, so pretty straightforward, right? All right, so